Our first speaker today is Wilhelm Winter from the University of Münster. He's going to tell us about paper pooling models of the car element.
Thanks, David. Thanks to the organizers for the invitation together, including me, especially to the Infin. Been doing a terrific job, I think. So what's in the background of this is always the UCT problem, obviously. Equivalently, this asks that whether every separable simple usual nuclear C-star algebra has a Cartan subalgebra or a diagonal, and I can't prove or disprove that, unfortunately. But what I was then wondering, if you know your C-star, your ambient C-star quite well, say it's the part to infinity or the Kunst algebra 2, how difficult is it to find Cartan subalgebras or diagonals? How many are there? How well are they concealed? Is it that we can't find them in general? Is the problem that they're not always there, or are they just very well hidden? And then, so here, the problem you can ask very vaguely in A classifiable. How hard is it? Is it find trans or angles with, say, with some prescribed properties? Okay, and one thing I'm particularly interested in is say the car algebra, the Treff algebra, when some these algebras we know and like it, we think we've classified. And I'm also interested in E having counter spectrum and X or counter spectrum, and there's several reasons why I'm particularly interested in counter spectrum. So one reason is you want a universal space, and in particular you want a space that's invariant under taking tensor products or taking products, which the counter spectrum does, and then also as a long-term goal, I think it's not completely unreasonable to ask for conditions on Cartans or diagonals, so that you might classify at least some of them. We don't have to classify all of them, of course, but maybe we find conditions so that we classify them with some sort of K-theoretic variance, and then we certainly in a better place if we can make our commutative subalgebras more accessible to K-theoretic methods. The counter spectrum is the rearrange zero case. That certainly has a better chance of doing that. All right, so some examples. One, of course, e to infinity, the standard diagonal in n to infinity, and the car algebra n to infinity in turn sits in O2, and then this is a diagonal, and this is a Cartan on the diagonal. And then we have Blackadder's example, C of x times the circle in n to infinity. His famous diagram in the car algebra. Then Jernburg found something similar in O2. This is also a diagonal. And then with Philip Civil, I don't know. C of x, so x the Cantor space in O2, and then Sam having Philip Civil push this to ON, so this is so we found that and then Mitchell and Spielberg found these very nice examples. Here C of x, and input them. We can put this as a Catan, but not as a diagonal. Diagonal into B theta. B theta here stands for this Efros Shen algebra, which has the same. It's an AF algebra which has the same K0 as the irrational rotation algebra E theta. Okay, so this is. And then there's here. There are examples. There's one example by Gwyn Evans and Eden, where they have C of x and they put it into a mystery C start with B, and B wants to be the car algebra, but what they do is they can show that this is Catan and also not diagonal. And B has lots of nice properties, has the right K theory, but they don't know if it's that stable, and so they can't quite apply classification. However, if you then tensor this B to infinity and this with n to infinity, then you still have a Catan which is not diagonal, and this is then isomorphic to n to infinity by classification. So we have an example of this. So this is what we don't have up to now. There's no diagonal which is neither a which is a proper diagonal, but which is not conjugate to the standard diagonal in n to infinity, and this is about your Rico is here. N to infinity, a non-standard kind of spectrum. So kind of spectrum. So this is this D is C of X, and non-standard means it's not in what's called an AF diagonal. It's not a diagonal that's compatible with the standard inductive limit structure where into infinity.
You mean standard or any,
Say again.
you mean standard or any,
Well, by standard,
It's the same.
non
Yeah.
AF. So by standard, I mean it's an AF pattern. And all of these are conjugate. This is normal.
So
They're
so
conjugate.
there's no sequence of parameters with theta advice, so if you take either of those, you get something against.
Yes.
Yes.
All of these are, or all of these AF diagonals, are conjugate. Yeah, as I say, it's powers. Fairly old example. So, yes, so this is what we have. And, already said why I was interested in this. I also have to say that about a year ago, I already thought I had an example like this, and I talked about this at some point. But it turned out to be non-regular, which is not so great if you want. So I was quite motivated to sort this out, to find an example like this. And then with rigorous after a long quest, we did. So I'm quite sure that this now works. And of course, if you want to aim towards any sort of classification of whatever type of diagonals you have in mind for say the car algebra, then the first thing you need is example separators, and you won't be able to see any structure. This is an example. So we want how to go. What's the proof? Some elements of the construction. So we want E in M to infinity, and we want this to be non-AF. And for this, it would be enough to have a chance spectrum diagonal which has a unitary. So we need a unitary moment, is it? Such that you with an infinite orbit. And by infinite orbit, I mean we have a unitary normalizer, and this induces a homeomorphism of the space X. And then we look at this homeomorphism, and if this has an infinite orbit somewhere, then this diagonal cannot be AF. Compactness argument. But of course, something like C of X with just this unitary, this won't work. This won't work since we always have something left in K1. K1 is the trivial, and then you can try something like the theta algebra of say C of X, and the two is this is the standard diagonal 2 by 2 matrices. And then you put your unitary U into a 2 by 2 matrix where you get the U, or right corner, you put U star, and then you throw in another unitary, which is just a flip. And then you put this into C of X cross product with Z, and then that you take the cross product with Z or 2Z implemented by this flipping unitary. Okay, and well, I want to put this inside C of X or Z, and then has a 2 by 2 matrices. Then take this, and then hope that you can show that this is the target for maybe on a good day or manufacture the card for orbits. And what you then get is a so then have C of X what product with Z, say you have some minimal action, the kind of minimal system, and then you have a Z2 action, say sigma. Z2, and suppose this Z2 action comes from an action on X, on the space X, and you want it to be compatible with the cross product, so you want that it anti-commutes with phi. But we also want a diagonal, so we want C of X right there as diagonal, so the action has to be free. And in particular, mean that sigma and also phi sigma have no fixed points. So this is necessary for freeness of the action and for the end result being diagonal. And then you observe that this condition is not possible if phi is equicontinuous. So, for example, if you start with phi the odometer, then you won't be able to make this work. Okay, but on the other hand, from this
Did you
here,
like the sigma has no fixed point?
say again,
Did you like the sigma has no fixed point?
sigma and phi sigma.
How can sigma have no fixed point if there is two?
You mean phi and phi sigma?
Yeah, that must be it. Yeah. That's it.
Who's giving the talk? Sigma is so sigma is an action on X.
Okay, so yeah,
If it comes from an action on X, I misuse notation.
Yeah, yeah. All of the factors, all of it, I said, sorry. Yes.
If B also has no fixed point. It was minimal to begin with. So P is minimal in particular of fixed points. The jokes you get to make in a math talk. Excellent. Like P has no fixed point. All right, so we want this, and then if it's it's an action that comes from the action on X, and I misuse notation here, and it anti-commutes with P, then really what you get is a cross product of C of X with the dihedral group Z times Z to Z. This is then and C. And for this thing, we also need to be able to control the K theory. So K theory. Not only we need to control it, it's supposed to be the K theory of the cars, or at least not so far off. Okay, and that's why it's a pity that we can't use the odometer, because for that we know how to we know what the K theory is, and it's already quite close to the K theory of the car. So that it's not something we have, and so by now we have a we have a rough picture of what we expect from our setup from phi and sigma, and then we go to symbolic dynamics. And in particular, you look at subshifts. Of say 0, 1. That will then be the shift, and then we get the subshift of this. And then the way this works is we have some sequence P bar in 0, 1 Z. This is our initial sequence, and then X is just this sequence T bar, and then we take powers of phi of that, and we close this and take it should be and again Cantor system. And their criteria in terms of this starting sequence P bar, their criteria of when this is minimal, and their ways of computing the K theory of that works so very nice, but we want more. I have to. So now we have a bit of a wish list for our initial sequence T. One now is that T is what's called uniformly recurrent, And this then makes it minimal and uniquely erotic, the associated dynamical system. Okay, there are many many sequences like that. We also need our sigma, and sigma, this is there's a canonical map sigma. There's several canonical maps sigma on this space, and one thing you can do is just flip. You have time reversal, but you could also reverse zeros and ones, like a bit flip, and you can combine the two, and that's then anti-reversal. And so we want X is variable under anti-reversal sigma. So this is change the time, and you use what zeros for ones and ones for zeros. And we want that we want no fixed points, and want neither sigma nor phi sigma to have any fixed points. And in particular, this means that phi can have there's only, say, few what's called anti-palindromes. Right? You take the word in zeros and ones and you reverse it, and you flip zeros and ones, then if you arrive at the same word, that's called an anti-palindrome. And we want only few of those, like finitely many, and then phi sigma and sigma water fixed points. And we also want that K0 0x. Product, the dihedral group is say that 1/2. That failing, how about close to Z1? What I mean by that, and I want K1 is to be 0. And then the claim is that such a P exists, and we're both not experts in symbolic dynamics, and we kept discussing with ChatGPT and also gave it this wish list, and so no, you're praised for asking an excellent question. So of course you can do it. Gives you some sequence. It doesn't work. Then you're praised again for fetching that. It never works. It's horrendous. That guy. Anyway. So do I have yes, excellent. That's good. So then you keep looking, and eventually you find something, and that's the paper folding stop shift. And what happens is this: you take a sheet of paper, okay, on the side, and then you fold it over. Say then you have this, and then yeah, but fold here, okay, and then you fold it again, like this folded paper, fold it again. This. And fold. Then this. This. Okay, and then you fold it again. Yes. And do this. And of course, you have to always keep track of these guys. And this. And then you keep doing sheet of paper. You can't do this more than 6 or 7 times. And with a whiteboard, you can only do it 2 or 3 times. And then you run through your paper and you look at the left turns and at the right turns. So here you have the left and another left, and then you have a right and then a left, and so on. And you keep track of that. And then this gives you a sequence. And in this case, it's a sequence 1, 1, 0, 1, 1, 0, 0. And goes on, and you keep folding. You can also unfold your paper and mark the downwards creases and the upwards creases with ones and zeros. And then you can get the sequence. This is that D bar. This is now a sequence indexed by the natural numbers, but then you can extend this pretty standard to some T bar by infinite sequence, and you're not so comfortable with this folding picture, then you can just define this recursively. You can take D1 is 1, you start with 1, first fold, and you start with the empty word as you like. And then once you have Tn, the word after n iterations, after n folds, then you write down Tn plus 1, and this you get by simply taking the word Tn that you already had, then you add a new fold in the middle. This is 1, and then the rest of the word is just Tn anti-reversed. So it's Tn hat, and Tn hat. This is the anti-reversal of here. Okay, and once you've done that, then you take your sequence D, you take its shifts, and you get this. The subspace of 0, 1 to the z of this product, we close it up, and then we have a counter-infinite system, because this sequence it does satisfy all of these properties that I asked for, these first ones. There are a few anti-palindromes, and we have to check that, you have to show that, but this can be done. And then you compute a knot of the And then it turns out that this is, I mean, this was already done in principle in a paper by Brottley, Evans, and Kishimoto, and they would have arrived at Z1/2. Their method would have given us Z1/2, but then there's a later paper by Klaus Thompson, and his method would give us the summand of Z2, the torsion summand, and then we were very confused, and then until we found this little very polite remark in Evans's paper saying this summand was overlooked in Brottley, Evans, Kishimoto. And then we went to Thompson's proof, and it looked all fine, except for a small typo that then also had to be sorted out, because we also need to keep track of the order, position of the unit. But this is really what you get, and K1 is indeed 0. So that's not too bad, because now we can just take C of x times the helical group and handle this with n to infinity, and then this is set half as we want. Then and then C of x tensor to infinity contains it. C of x is called product tensor n to infinity. This is the diagonal you look for. So this is then isomorphic to n to infinity by classification, because all the other properties that you need for classification are satisfied. Okay, so this is the example we want. And then you ask what other properties does this have, and is it the only example, or surely not? But yeah, other examples, how can you distinguish them? And first thing one does when you have a kind of spectrum diagonal, you take the tensor product with itself, and then you get a diagonal again, just again kind of spectrum. But then how do you make sure that it's not the same? Well, it turns out that if you if you take, say, C of x times itself, and you then take the product